Aluminum is one of the most versatile metals in the world. It can bend almost like paper, yet it is strong, durable, and resistant to corrosion. It is used to preserve food, cook meals, build vehicles, manufacture electronics, and create countless everyday products. But how is aluminum foil actually made? In this video, we will follow the process as millions of tons of mineral are transformed into the thin, flexible rolls found in kitchens around the world. Aluminum foil became widely used during the 20th century and was initially popular for wrapping products such as chocolate bars. Since then, it has become a common kitchen material because it is lightweight, water-resistant, and capable of helping control heat. Its shiny surface reflects thermal radiation, helping food retain heat for longer. For centuries, producing aluminum was so difficult and expensive that the metal was once considered more valuable than gold. The first step is obtaining pure aluminum. Aluminum is extracted from bauxite, a reddish mineral found in large quantities in Earth's crust. Most bauxite is mined in tropical and subtropical regions before being transported to an alumina refinery. From this red earth, factories extract a fine white powder known as aluminum oxide, or alumina. This material will eventually be used to manufacture aluminum foil, beverage cans, and construction materials. Aluminum is the third most abundant element in Earth's crust. Bauxite is the main ore from which aluminum can be extracted economically. Some of the world's largest bauxite mines are located in Australia. A major mining operation can extract around 25 million tons of bauxite every year. Before miners can reach the valuable ore, they must often remove layers of soil, vegetation, and rock. Powerful excavators and haul trucks move thousands of tons of bauxite every day. High-quality bauxite may contain more than 50% aluminum oxide, but it also contains clay, sand, iron compounds, and other unwanted materials. Mining and washing bauxite requires enormous quantities of water. At the processing site, the ore enters massive washing systems. Water removes clay and separates material containing relatively little aluminum from the richer portions of the ore. The washed ore is then crushed and ground into a fine powder. This increases its surface area and makes the chemical extraction process more efficient. The powder is transported to an alumina refinery, where the valuable aluminum compounds are separated from the rest of the mineral. This is accomplished through a chemical treatment known as the Bayer process, which has been used for more than a century. Finely ground bauxite is mixed with a hot, concentrated solution of caustic soda under high pressure. The liquid dissolves the aluminum-containing compounds while leaving many unwanted solids behind. The mixture is filtered, separating an iron-rich residue known as red mud. The remaining liquid contains dissolved aluminum compounds. It is cooled and treated until aluminum hydroxide crystals begin to form. These crystals are filtered, washed, and heated inside large furnaces. This stage, called calcination, removes moisture and converts the material into alumina. The result is a fine white powder that serves as the starting point for metallic aluminum. Large loading systems can fill ships with more than 77,000 tons of alumina. A shipment of that size can eventually produce roughly half that amount in pure aluminum because oxygen and other mass are removed during processing.
To turn alumina into metal, the oxygen atoms holding it together must be separated. The practical way to do this on a massive scale is by using tremendous amounts of electricity. The white powder travels by conveyor into an aluminium smelter. There, it is transformed into molten metal through an electrolytic process. A large smelting facility may contain hundreds of steel reduction pots arranged in long production lines. Inside each pot, alumina is dissolved in a molten mineral bath at about 1,740 degrees Fahrenheit. Well above aluminium's melting point, a powerful electric current passes through the mixture. The electricity breaks the chemical bonds connecting aluminium and oxygen. The oxygen reacts with carbon near the top of the pot, while the denser molten aluminium collects at the bottom. Producing primary aluminium requires enormous amounts of power, several times more than producing the same amount of steel. Electricity alone can represent a major portion of the total production cost. Molten aluminium is also extremely reactive. Contact with water can cause a violent steam explosion. Aluminium does, however, have one major advantage. Once produced, it can be melted and reused repeatedly. Recycling aluminium requires only a fraction of the energy needed to make new metal from bauxite. To meet global demand, smelters operate 24 hours a day, 7 days a week.
A large facility can produce more than 170,000 tons of aluminum per year. The molten metal must now be removed from the reduction pots. Each pot may produce about 1.5 tons of aluminum per day. Specialized vacuum equipment draws the liquid into large, heat-resistant crucibles. The crucibles are transported to the casting area. Before casting, the aluminium may be treated to remove gases and impurities. Alloying elements can also be added to give the finished metal specific characteristics. The molten aluminium is poured into molds to form enormous rectangular slabs called ingots. Water cooling systems remove heat from the molds and accelerate solidification. Once cooled, each ingot can measure nearly 15 feet long, about 5 feet wide, and weigh close to 9 tons. Overhead cranes are required to lift and position these massive blocks. Before rolling begins, a milling machine removes about 1/8 of an inch from the ingot's surface. This eliminates oxidation, casting marks, and other impurities, creating a smooth and uniform slab. These ingots are then transferred to factories that manufacture aluminium sheet and foil. Making foil requires repeatedly compressing and stretching the aluminum until the thick slab becomes an extremely thin sheet. The next major stage is hot rolling. The ingots are heated to a controlled temperature and pass through powerful rollers. Each pass squeezes the metal, reduces its thickness, and increases its length. The slab can become hot enough to stick to the rollers. To prevent this, a cooling and lubricating liquid is sprayed across the equipment. The mixture may contain about 95% water and 5% oil. Starting at around 18 inches thick, the slab becomes thinner after every pass. It may travel through the rolling mill between 12 and 16 times. Different sets of rollers gradually produce flatter, thinner, and more uniform aluminum. Eventually, the ingot becomes a sheet only a fraction of an inch thick. It is then wound into a massive coil and sent to the cold rolling mill. During cold rolling, the aluminium passes through additional rollers without being heated to the same high temperature. This reduces the thickness even further, while improving the surface quality and dimensional accuracy. The sheet is pulled through the mill under tremendous tension. At this stage, it is becoming so thin that it could tear if the pressure, speed, or alignment are not precisely controlled. Coolant prevents the aluminium from sticking to the rollers and removes heat created by friction. Sensors continuously measure thickness, tension, flatness, and speed. As the foil becomes thinner, manufacturers may place two layers together and roll them at the same time. This creates the familiar shiny and dull sides of household aluminium foil. The surfaces touching the polished rollers become shiny, while the sides pressed against each other develop a matte finish. Despite their different appearance, both sides are made from the same aluminium and generally perform the same way during ordinary cooking. After rolling, the foil undergoes annealing. The large coils are heated inside a furnace for a controlled period. This reduces internal stress and softens the metal, making it easier to fold, shape, and wrap around food. Annealing also removes traces of rolling lubricant. Finished household foil can be only a few 10,000ths of an inch thick. Heavy-duty foil is made slightly thicker to provide additional strength. The enormous master rolls are transferred to slitting and rewinding machines. Rotating blades cut the wide sheet into narrower strips for household, restaurant, and industrial products. The foil is then rewound onto cardboard cores. Automatic machinery controls the length and tension of each roll, so the material remains smooth and does not wrinkle or tear. The rolls are trimmed, inspected, and packed into familiar cardboard boxes. Many boxes include a serrated cutting edge that allows users to tear off the required length. Quality control teams inspect the foil for tiny holes, surface defects, uneven thickness, contamination, and weak areas. Even a small variation can affect how the foil performs during packaging or cooking. Once the foil passes inspection, it is packed into shipping cartons and sent to stores, restaurants, and factories around the world. What began as reddish bauxite buried beneath the ground has now become a sheet of metal thin enough to fold with your fingertips. Through mining, refining, electrolysis, casting, hot rolling, cold rolling, and annealing, a massive block of aluminum becomes one of the most useful materials in the modern kitchen. It withstands high cooking temperatures, takes the shape of almost any container, and can be recycled when local recycling systems accept it. If you enjoyed learning how aluminum foil is produced, like the video and share it with someone who may find it interesting. Subscribe and turn on notifications to continue discovering how everyday products are made.